This is a lecture on 4-2, the addition rules for probability. We're going to talk about one definition, which is included in your definition handout. Mutually exclusive events. Two events are mutually exclusive or disjoint events if they cannot occur at the same time. For example, randomly selecting a female student versus randomly selecting a student who's a junior. Now, these events are not mutually exclusive because it is possible to find a junior who happens to be a female student. On the other hand, randomly selecting a person with a type A blood and randomly selecting a person with a type O blood. These are a mutually exclusive event because it is not possible to have a blood A and a blood O type at the same time. So the probability rules that I'm interested in discussing has to do with an OR statement. This is rule number 4 in your handout. And one of the good ways of having a picture of this is a Venn diagram. A Venn diagram, just like a tree diagram, is just one of the tools that will help you along with in chapter 4. A Venn diagram is a representation of a probability of events. Because I'm interested in drawing something disjoint, I'll draw this as the probability of A, and completely separate, I have the probability of B. Now, on the outskirts, I have my sample space, which has to be 1. So the whole box has to be 1, and whatever's inside has to be parts of it. I'm going to continue and take a look at 4-17 in the book. In the United States, there are 59 different species of mammals that are endangered, 75 different species of birds that are endangered, and 68 species of fish that are endangered. If one animal is selected at random, find the probability that it's either mammal or a fish. So I don't need to draw a full diagram for this, but I do want to write something down. So I have 59 mammals. 75 birds, and 68 fish, types of fish. I'm interested in finding the probability of mammal, or fish. Now, in order for me to find the number in my sample space, I just take out my calculator and figure out how many of the events I have. How many animals am I talking about? So I take 59 plus 75 plus 68. I end up with 102 endangered animals. This is my sample space. So, if I'm interested in mammals or fish, I can take 59 out of 202 plus the fish 68 out of 202. We know how to add fractions, meaning that you could have added the mammals and the fish first and then divided by 22 because the algebra comes out the same. What you probably want to do is step away from fractions as your final answer and rather give me a decimal approximation correct to 4 decimal places. So the approximation is 0.6287, and then the next one is 1, so I'll round this down if you want. So technically this is an approximation, but it is not wrong to write an equal sign because it is a probability. You can always change this to a percentile and give the final answer in terms of percents. Next example. is 4-20. A single card is drawn at random from an ordinary deck of cards. Find the probability that it's either a 9 or a diamond. So note, my event, my probability experiment, is deck of cards. Drawing a card from a deck. I know that the sample space has 52 cards because I'm aware of this particular sample space. Now, the probability that they're asking us for is find the probability that it's either a 9 or a diamond. Now, the question that you have to ask yourself is there such a thing as 9 of diamonds? And the answer is yes. So, the formula that you have up here, which is formula number 4 on your formula handout, will not work anymore because this one is for mutually exclusive events. This event, the 9 and diamonds, are not mutually exclusive. What happens is you need an alteration to your formula. The alteration of the formula is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection. We'll write it as an AND. Now this particular rule makes a lot of sense if you draw this as a Venn diagram. If this is your A and this is your B, so I'll label this as a probability of A versus a probability of B, what you have is you have this intersection. Now if you are taking the probability of A and you're adding it to a probability of B, notice that this intersection is counted twice. One when you're counting the probability of A, and then the second time the probability of B. Therefore, what we need to do is we need to take out one of those intersections. To finish this problem, well, I know that there is 4 9s in a deck. So the probability of getting a 9 has to be 4 out of 52. Now, as far as diamonds, there are 13 diamonds. But notice, the 9 of diamonds was counted twice. Once for when you were counting the 9s, and the other time is when you were counting the diamonds. What you have to do is you have to take that one out. That's a minus. The final answer for this problem is therefore 16 out of 52, which can be approximated to 0.307 and then 69, so I'll round this to a 7. If anything, this is the only issue with this particular chapter, so I'm going to do one more example of this scenario. The example is 4-21. In a hospital unit, there's 8 nurses and 5 physicians. 7 nurses and 3 physicians are female. If a staff person is selected, find the probability that the subject is a nurse or a male. So, in order for us to see what is going on in here, the best scenario is to draw a two-way table. A two-way table will help us along the way in Chapter 4 and really throughout the semester. We'll see those again at the end of the semester in Chapter 11. And so what I want to do is I want to give it some rows and some columns. So I have nurses, I have physicians. A nurse can be either a female or male. Same thing for the physicians. I'm going to go ahead and read the problem again. In a hospital unit, there's 8 nurses and 5 physicians. So what they gave us to start with are the totals. 8 nurses and 5 physicians. If anything, I know I have 13 people on staff. 7 nurses and 3 physicians are female. So 7 nurses and 3 physicians are female. If the staff person is selected, find the probability that the subject is a nurse or male. Now, in order for me to answer this question, I'm going to complete this two-way table. A two-way table, just like a Venn diagram, just like a tree diagram, is a tool. The rows need to add up, the columns need to add up, all of the totals can be figured out. If I have 8 nurses and 7 of them are female, therefore I have 1 male nurse. Physicians, if I have 5 physicians, 3 of them female, 2 has to be males. Therefore, I know I have 10 females on staff. I have 3 males on staff. Together, they add up to 13. Notice the rows add up to 13, the columns add up to 13, so this is your grand total. In order to find the probability of randomly selecting a nurse or a male, I can either go through the formulas or I can look at this two-way table and figure out just exactly what they're asking for. If I need a nurse, I have this 8 people, but I also need a male. Now this male has already been counted, so I need to count this one. Now if you didn't quite see the 10 out of 13 right away, you can jump into formulas and go a little bit slower. The probability of getting a nurse, 8 out of 13, plus the probability of getting males, I have 3 out of 13. Now minus the intersection, meaning male nurse. How many male nurses do we have? Well, there's my male nurse. Notice 8 plus 3 is 11 minus 1, there's my 10 out of 13. However you look at this, the final answer is 10 out of 13, which approximates to 0.7692 followed by a 0.